simulations to make your molecular models. So in lab, our first experiment we will be doing online is experiment number 10, which is using molecular model kits to determine geometries and hybridization of molecules. Now, obviously, most of you probably do not have a molecule kit at home. If you do, please go ahead and use it, as it's a really good resource for you. Instead, we have for you an online simulation that will be just as good in terms of getting to play with the model kits. So I'm on this website, phet, which is a part of the University of Colorado. It may look a little inelegant, but trust me, this is some of the best software we have to make sure everybody gets free uses of this material. So in your assignment, I have links to both of the molecule shapes that we're going to be using to play around with the model kits for today. However, I will show you how I got there. So if you just Google phet, P-H-E-T, it will be one of the first things that comes up. You can go onto their website, go to simulations, hit chemistry, and that will bring you to this site right here. Scroll down and we have two options available to you, molecular shapes and molecular shapes basics. I'm going to go straight to molecular shapes because this actually gives us more than the basics will give us. So you can click on molecular shapes and we'll take you to here. Please just hit play. It will start the simulation and we have two options here. We can just play with a model where we can rotate. So I'm holding my mouse down and just kind of spinning it around, and allows us to rotate our molecule in 3D space. But a few features I want to show you real quick. Please make sure you highlight the molecular geometry as well as the electron geometry. Now, you may have learned these as different names. Sometimes this is called electronic shape or molecular shape, but the same thing still applies here. What we're talking about is how many electronic groups there are and the name that goes with that versus how many molecular groups there are and the name that goes with that. In your lecture, again, you'll get more detail in terms of how we go through and memorize these and things like that. The other thing that might be useful that you might want to see is the bond angle. And what this does is, I'm just going to rotate this around so you can see it. The bond angle is the angle between the different atoms or different portions of the molecule from the central atom. So right now we're looking at a molecule that has a central atom and two atoms on either side of it bound. Now, the example that you may be familiar with is if we have a double bound molecule like this, this would be an example of CO2, where the purple ball is the carbon and each of the each of the gray balls is an oxygen. We can see that CO2, even though there are double bonds present, this is still a linear molecule in both the electronic and molecular shapes. We could do an example where we have water, for example. So what I'm going to do is I'm just going to X out all my bonds, and we'll start with and pretend that this central atom here is our oxygen, and I'm going to add two bonds to it, which in this case would represent our hydrogens, but we know that oxygen has two bonds and two lone pairs, so I'm going to add two lone pairs as well. So I'm going to rotate this around so that we can see it a little more clearly. Oftentimes in class you've seen me maybe make this shape before where you could pretend this is you. If you make this shape, this would be your core, and if you stick your feet out in front and behind you and you put your arms in the air to the left and to the right, this would be the shape you would get. The two lone pairs would be your hands and the two hydrogen atoms would be your feet. Now I'm going to rotate it a little bit this way so that you can see it in this direction, as well as the traditional way that we represent, excuse me, the traditional representation of tetrahedral looks something like this, where we have one up, oops, here we go, there we go, one up and one straight to the side. These are both in the same plane. I could take a knife and cut through both of these. We have one of our lone pairs behind and one of our lone pairs facing front. This is the traditional way we represent a tetrahedral molecule. Again though, if you wanted to play with it in terms of how you could hold it, you could use your own body as a way to represent it, we would look more like this, where here are your 2 feet standing front and back, and here are your 2 hands. So this is a really good molecule kit that you'll be able to play with during lab to help once you've drawn out your Lewis structures. If you want to see what the shapes would look like and kind of be able to visualize it, you can use that. The other option we have down here are real molecules. And so in this we have a number of real molecules. Now some of these are actually from your lab itself, and that's fine, and I would still expect you to go through and draw these molecules out so that you can see them. But here is NH3. We know that nitrogen likes 3 bonds in 1 lone pair. So we can now look at the geometries for both the electronic and molecular. We can see electronic geometry is still tetrahedral, right? Here's that 4 electron groups around our central atom. I can put it back in the little shape we had before, right? 2 feet down here, front and back, 2 hands left and right. I'll put it back in its traditional drawing, which is like that. And that we see that the molecular geometry, because of this lone pair, is not tetrahedral, but we see that the electronic geometry is actually trigonal pyramidal. So you can go ahead and utilize this software as a way to kind of be a stand-in for your model kits while you're doing your lab today. So lots and lots of really helpful examples for you here. There are also videos showing you where I will go through and do a few examples from our lab manual as well for you to work with. But this is a really handy, useful tool to be able to utilize and visualize the different molecular and electronic geometries for these molecules.